Thank you for checking out my video around TLA and TLC for using an automated tool to draw a specification. I think this is an interesting technique for even the simple systems where we would typically use whiteboards to sketch out our ideas. Instead, we simply describe our ideas and let TLC draw the pictures for us. And then TLC can actually tell us things about our specification at the detail level, so we can think abstractly and lay out the various pieces of our designs, and then let TLC draw the pictures and answer questions about those pictures. I'm planning to do a follow-on to this video where I take more of a computer science-y idea like sorting and do a similar kind of method. This is more of a abstract, let's think about just a system, a product, an idea, and can we use this quote-unquote academic rigorous tool, this formal method, for something that's just a whiteboard. So this is my recasting of a whiteboard session. I'd love to know what you think. If you have any ideas, there is a written form of this video. You can follow on with the spec from GitHub, or you can check out the written where I go through all of the details and the motivation for how this spec came to be. Thank you for stopping by and enjoy TLA+. All right, so this is where we are. We're starting with an empty specification. We've created the spec. We've created an empty model. And we're going to go add our TLC options, go into parameters, and this is where we want to add our magic dump line. So that's right here. Okay, we're starting with an empty spec. We're going to create our empty model. Here's our empty model. We're going to go to TLC options because what we're really interested in this style of design is making pictures of our design. So we're going to have TLC make our pictures. So this is documented in the notes, but these are the various options that we want to dump, and then we're going to call it the soda dot dot. So the soda machine dot dot. Okay. We're going to go ahead and hit run. There is no model, but if we do an ls, we'll go into our model directory. We can see there's a soda dot dot. Okay, it's empty. We're going to put a watch on that. Which is this FS watch, which is just going to draw the picture every time the file changes. And then let's go ahead and run our model. Make sure that's working. Okay. We have that new soda.png. And there we go. We have our empty specification. And as we work through the specification, we'll see the model redraw, and we'll get to kind of have the machine check that it's drawing the picture we think is intuitively correct. Okay, so let's go ahead and get started. The beginning of any TLC spec starts with three things. It starts with a spec, starts with next, and init. And we'll just fill these things in as we go. The spec is simply boilerplate at this point. We want to start with init and always next over the vars. And we want weak fairness over the vars for the state next. Okay. We need some basic libraries, extends, integers, sequences and TLC. Save. All right, we got some compilation errors. So let's just start with our init. Now, remember we have the soda machine. So what were the things in our soda machine? Let's make those variables. The variable was I have soda. There's the soda machine itself. There's I want soda. And finally, there's how much money I have to buy soda. And all of these are our sequence of variables. I have soda, the soda machine, I want soda, and the money itself. And so far, this is all just kind of boilerplate. It's just sketching up what our system is, what is the domain of our system, so what are the variables that we consider, not what we're going to need to build it. This is just what we need to kind of have our discussion. Remember, we're just sketching out an idea, thinking about how we would interact with a soda machine to solve this problem of having soda and wanting soda. Okay. Subsequent specs, we're going to try different levels of abstraction, not so much the discovery process, but more like how do we actually implement something. So TLC and TLA plus lets you have this sliding scale of specificity, or how specific you want to get. It lets you express things at a very high level of abstraction, lets you express things at a very detailed level, and then you can decide exactly what you want to check. So let's fill out our init case. We're going to say and I have soda. It's false. And I want soda, and it's true. And the soda machine has 5 sodas. And the money, I have 1. I have 1 money. Now, what kind of things are we going to want to check? Well, we're going to want to check, it's typically called the TypeOk or the TypeOk or the TypeInvariant. The money should always be greater than or equal to 0. You can't run out of money. You can't spend money you don't have. The soda machine must always cannot have negative soda. The soda machine also cannot sell soda that it doesn't have. And I want soda should either be true or false. It should be in the set true or false. Likewise, I have soda should be in the set of true or false. And that's pretty much our system. Now, what kind of things do we want to check? Well, we want to check that I eventually get soda. That's kind of what I care about. So let's see, what would this mean? This would mean that always I have money implies eventually I have soda. And as we'll go through the spec, we'll see that this is slightly not true, but this is what we want to express. We want to say, hey, if I have money, then I can have soda. I won't have it immediately, but sometime later, I'll spend some money or whatever it takes, and I'll get some soda. So that would translate to always I have soda, I have money implies, or then eventually I have soda. That's really kind of the goal that we're going for. Okay, so let's save it. And what's this upset about? I have soda. Some false. These are assignments. Okay. So this is not, init is defined as the equation of this is true, that's false, that's true. So, okay, thank you. TLC checked our syntax. So now let's have a basic Now let's think about, we have our initial condition and we have our spec. What can we do with this so far? Well, let's just say nothing happens. And that's it. What does I have money mean? Well, we need to actually check. We need to tell TLC, what does I have money mean? I have money means, or is defined as, my money is greater than 0. All right. So let's just run this. Let's go to our model, choose temporal formula. The temporal formula that we want is spec. Save that. Run it. Okay, it's going to run our spec. It created our state diagram, and there's our state diagram. So we have one money, we have soda, we want soda, and the soda machine still has money in it, and nothing's changing. So there's just one state. That's it. That's our whole system. Now let's ask it to check if this is true. I eventually get soda. So we'll take this invariant. Sorry, not invariant. We will put it in our temporal properties. Finish. Okay. And then we do have an invariant, all of the things about money here. And we place this in the invariance slot. Okay. We run it again, and this is going to fail because we never succeed. We never actually get the soda that we want, even though we have money. So, did our drawing change? Nope. Our drawing did not change, which makes sense. We haven't added any new states yet, but we don't eventually get soda. So we haven't shown a system that fulfills this yet. Okay, so let's do something more than nothing. So instead of unchanged vars, what could our system include? Well, we could say either or I have soda, or I want soda, and I have money, or nothing. Okay, so what if I have soda? If I have soda, then in the next state, I have soda equals false. Because if I have soda, I'm going to immediately drink it. And I want soda in the next state is equal to true. Because the moment I no longer have soda, I want it again. Finally, that's it. If I have soda, I drink it and I want more. So we have to tell our state machine, okay, fine, well this has, you're changing I have soda and I want soda, but double check, are you sure you don't want to change anything else? This is that double check. So we get to say, yep, I don't intend to spend any money here, and the soda machine doesn't change. So this is a nice double check that the system you're trying to realize checks. Okay. Let's run our model again, see if our picture changes. Temporal properties are still violated. Let's just turn this off for now so we can keep sketching. Okay. Right. Now, why did the picture not change? Well, the picture didn't change because the initial condition, false, I have soda, this is false. So this never runs. So our system does nothing. So let's describe what happens when I do have soda. So when I want soda and I have money, we have to declare this above, kind of like in C. Okay. Well, when I have soda and I want money, when I want soda and I have money, then we simply put money in the machine. Put money in machine. And that's it. Okay. What else then? What does put money in the machine mean? Put money in the machine is defined as, or the soda machine has soda, or the soda machine does not have soda. The little twiddle is the not. Well, if the soda machine has soda, then my money's going to go down because I immediately spend one money. So the next state will have less money in it. And I have soda in the next state will be true because as soon as the soda machine has money and I put my money in, it gives me soda. The soda machine in the next state has less soda in it. And I want soda in the next state. So the same state where I have soda, I also don't want soda. So you can see here that I have soda and I want soda are nots of each other. So one is the complement of the other. And this is something that kind of sketching the spec, we saw, oh, actually these variables are just related to each other. We probably don't need to express them separately. Let's keep them separate for now. Okay. The soda machine has soda. Oh, what does that mean? The soda machine has soda is defined as the soda machine has more than 0 soda. Okay. Put money in machine. Put money in machine. Okay. Let's run this again. Let's check our picture. Ooh, we got more states. Look at that. So we have money, we spend it, we have soda. Soda machine has 4 sodas now. It had 5. And then we have no money and we drank our soda and it's all done. So we ran out of money and everything's good. All right. So we got a nice little picture drawing our system. We have a nice little description that can be machine checked of what we wanted to express. Let's see if it satisfies our little requirement here. I eventually get soda. And let's run it again. Awesome. Do I eventually always get soda? Well, let's just play around with how much money we have. So if we have 2 money, what happens? We can run it again and go, will I still get soda? Well, nothing failed. So that implies, oh, there's more states now because we're spending more money. So that makes sense. But notice that money always runs out before we have soda. But we don't want to run this over and over and over. So let's just say, you know what, this system, run it for money from 2 to 10. So let's run our model and see what happens. We'll run this. Sits there and runs. It finds that we have, okay, so there are cases where, what is the error we're actually getting? Deadlock reached. So what does deadlock mean in our system? Our system can mean that we've run out of money. If we run out of money, nothing proceeds. So if we run out of money, if I have no money, we cannot buy soda, everything stops. You know what, in this system, that's okay. We're gonna let that be okay. What happens when the soda machine runs out of soda? Well, in that case, we'll be okay. So we're gonna turn off deadlock detection because we're gonna just state that we're okay with deadlocks occurring, with the system just stopping because nothing can proceed forward. So let's run this again. Okay, we got a temporal violation. So what would this mean? So this would mean that I don't have soda, I want some, and I have money. So the configuration that starts with more money than soda, so if we check our picture here, we can go to the system that has more money than soda and follow our states, follow the diagrams, go step by step. When we get to the end, money is 1, I have soda, I drink it, I still have 1 money, I don't have soda, I want some, but the soda machine's out. Recall what our temporal equation was. Always, when I have money, implies I have soda. Well, I have money, but the system cannot proceed. The system cannot give me soda that the system doesn't have. Therefore, we must also say, I have money and the soda machine has soda, implies I have soda eventually. And we run this, and our system checks. We got a picture, looks good. So we've been able to sketch a basic vending machine, and we've been able to show how TLC would draw the state diagrams for us and show us things about our system. And then we can even play around with different variables. We can sweep, we can sweep 2 variables. And what does this do? We can run this again. Ooh, something bad happens. Because I said you cannot assign a set, you have to assign like that. And we can run this, and let's see, what's our system look like? Well, what's our picture look like? Ooh, picture's all crazy. So if we zoom out a little bit, we have these various mixed initial conditions that when the money and the soda are moving separately, and then they create some ordered set of buys as we go through and drink all of the soda. And so it just sits there and draws out all of our pictures. Now at some point the picture becomes too large to draw, becomes you can't use this sketching method for every system, but for simple systems, for discovery, and I propose sitting in meetings just sketching out different ways of talking about what your systems should do or could do, and then try and ask TLC if that is a reasonable set of properties or invariants or whatever it takes. So thank you for watching.